Hey guys, today we're doing round 670, div 2, and well, when I was getting set up, like my entire taskbar just disappeared, so I am kind of starting late right now. So we're getting right into the contest, but before I do that, I will update the sub count as always, which I actually think is inaccurate because it says here I have at least 1390, but I clearly do not in analytics, so I'm not really sure which number to use. I'll just go with this one for now since it's been trustworthy. But anyway, yeah, now we should do the problems. So, given a set of integers, you have to maximize the value of mex a plus mex b. Okay, so let me get some stuff ready. So the way this is basically going to work is, as soon as Paint loads, is that the mex, to get a mex of x, you have to have all the numbers 0, 1, 2, 3, up to x minus 1. And so basically for us to have a mex of x in the first set, we need to have all these numbers. So we want to put as many of these numbers as we can towards the first set, and then we put as many of the remaining numbers as we can towards the second set. So it's basically maintaining, if we have 2 zeros, we can put both of them, we can put one in each set. Otherwise, if we have 1, then this mex is done. We can't do anything more with it because we don't have a 0 to put. So now we only focus on this one. So now we look at the 1s, so we have this. Then if we have 1, 1, then again we're done with this mex and we'll keep trying here. And if we have both, we can keep going with both of them. And if we have none, then we're done in total. So that will basically be how that works. The implementation will be slightly different. So what I'll do is I'll have a count array. Wait. Okay, the mex is at most n because there can be only, like for the mex to be n, every element has to be distinct, and it has to be 0 to n minus 1, so we can't do better than that. So we can only iterate up to n. It doesn't really matter, the complexity is going to be fine, whatever. But anyway, so basically cur is the number of sets we have where we can still add to the mex. For example, here cur would be 1 because we can't add to this one, but we can keep adding to this one. And if it was like this, cur would be 2. So basically the cur is the minimum of the count we have because we can't get any more subsets, so it has to be the minimum. And if we have fewer than what we currently have, then there's nothing we can do because like we don't have enough elements to continue the mex. Test cases. Oh, what now? What is it doing? Oh, 12. Wait, what? What is it doing? Oh, I guess that. Oh, it doesn't compile. What have I done here? Oh, semicolon. Whoops. Still wrong. Because it should be I, not X. I don't even know what X would be in this case. 5, 3, 4, 0. Okay, perfect. That was stupid. Okay, let's open the rest of my files. What's this? Why is there a 3 here? Is that a new feature? That'd be cool if it was. No, what does that mean? Oh, I guess we'll find out later. So we're given an array. Just keep the input from last time, 'cause it's the same thing. Okay, you're given an array. Find the maximum possible value of AI, AJ, AK, AL, AT. Seriously? That is very annoying. That is indeed very annoying. Why would you set a problem like this? Going 3 to the 5th. I guess honestly the smoothest way to do this is with dynamic programming, unless there's something I'm missing. So we're just gonna do that. So basically DP is index, number of elements taken, and something else which represents and then sign, because we want the biggest of each magnitude. Either we want the biggest positive number or the biggest negative number, and actually we want both of those. So I'm honestly not sure of a better way to implement this. Maybe there is just like sort it and do some greedy, but that's that sounds sketchy as hell and very likely to fail system tests, I guess. This is a typo? Must be a typo. Okay, so PIJK equals 1. Alright, actually it should be like DPI J0 equals some big number, and so the transition is we take an element or we don't. Okay, so 0, 0, 0 equals 1. It's all relatively standard. I will go over it later. Again, maybe there is some simple solution with like greedy and doing casework and stuff. So I guess there would be, because you can kind of brute force things a bit. But whatever. I guess this is more helpful anyway. I don't know. There's a thing you can do where you only have to care about like 15 elements at most, because you only care about the, or maybe it's worse than that. I'm not sure, because you only care about the extremes, namely the number of zeros you have, the biggest and smallest positive and negative elements. So that I guess works. So if you take this next equals dp I j k. Alright, actually, let's say if it exists. Say if it exists, then dpi jk times ai, then dpi plus 1, j plus 1, k 0 equals max that and next. And we do the same thing with 1, except we minimize it. Then dpi plus 1, j plus 1. Just do the same thing here. Because we also want to have the transition of not taking this element. Don't think we need that. Why? What's happening here? Why do we not take these? 5, 12, 12. Oh wait, 12 is right. Negative 5 million, negative 5 million, negative 5 million. But it's not taking these, is it? Now I'm confused. Oh wait, this should just be j, not j plus 1. Whoops. Yeah, because this is when we don't take another thing. What now? This is worse than greedy? Yeah, it is. What the hell? So what's going on here now? This is confusing. So I messed up some other transition, I guess. dpi plus 1, j plus 1, 0 is max that and min that. I plus 1, j 0. What's happening here? What is happening? Okay, so if we take, we have -1. If we don't, we can't. If this works, I'll be so confused. Okay, good. Wait, what? Why is it not printing? Okay, there it is. What? Yeah, small typo. Okay. That's just a fix on the statement. Not a big deal. Oh, wait. Because we can take 5 elements by the end. Whoops. N50. Yeah, that makes sense. Because we can take the ending elements. Okay, what the hell is going on here? It should be greater than or equal to. Okay, we finally have it. This should be less than, that's fine. This can be less than or equal to, this should be less than, this should be 6, this should be less than 5, I hope. It still works. Because there's no reason it would have to be less than or equal to, because we can't take an element once we have 5. Okay. That took a while. Alright. Centroids. Wow. Oh, wait, it's saying the number of tests. Oh, I see. Oh, that's cool. Wait, does that happen everywhere? Huh. That's useful. Fishing Prince loves trees, and he especially loves trees with only one centroid. Vertex 1 and 2 are centroids because the size of the largest connected. Okay. Now, Fishing Prince has a tree. He should cut one edge of the tree, means to remove the edge. After that, he should add one edge. The resulting graph after these two operations should be a tree. He can add the edge that he cut. He wants the centroid of the resulting tree to be unique. It can be proved that at least one such way always exists. Okay. Okay, so if n is odd, I think, then we don't have to do anything. Or we can just add the edge that we remove because Okay, for something to be a centroid, let's say like this. Or wait. Draw a graph like this, sort of bone, I don't know. Now both of these two vertices are centroids because the tree you get after removing them is very small. Or, like, the subtree you get is at most n minus 1. Okay. And let's see. I think there's only possible 2 centroids. Yeah. Okay, so this is the intuition that either there's one centroid, in which case, like, we're happy, we can just be done, or there are 2. And if there are 2, then what? So if there are 2, what can we do? Either we'll remove the edge between them or remove some other edge, I guess. Which one's better to do? So if we remove this edge and then we add it back, like attached to this one or attached to this one, for example, not both at once, but then like, obviously this is still going to be a subtree of size n over 2, and also this is still going to be a subtree of size n over 2. So if we remove this edge, we can't attach it back to either of the centroids, because again, the same thing will happen here. So can we put it somewhere else? Actually, if we put it anywhere else, we're still going to have subtrees of size n over 2. Because they'll just be connected at different points. So, okay, so removing this edge is like the worst thing we could possibly do, actually. Because it's impossible to do anything after that. And so we also can't move an edge into the same component because this will still be a subtree of size 2. So we have to remove an edge in one component and then add it back in some other component. And I guess that's what we have to do. Though I'm not really sure how to do it. So what guarantees that we don't have 2 centroids again? If we move any edge here, is it always possible? Should be. Is there like is there an actual solution to this, or is it just like, does it require even more DFS or whatever we do, or is it simpler than that? What does the sample say? So we make it 1 to 3, and then we add 2 to 3. Oh. Does that work? I guess it would. So what the sample does is it just, yeah, there's no way to have a sample that kind of doesn't give it away. So they remove they remove like a leaf or something, and then they just stick it onto this centroid. And so now this whole subtree will be size less than n over 2. And this subtree will now be of size greater than n over 2, and this vertex will be at the center of it all. So I think this will become the only centroid then. Because, okay, so first of all, this remains a centroid. It has to. Because the size of the subtree decreases and this just becomes 1, so it doesn't matter. And now that this size of the subtree is n plus 1, then there's no way anything here can be a centroid. So the only possible centroids are on this side, and this isn't a centroid. And now we have, because we have this, and we have this vertex, like, this subtree is of size m minus 1. So this subtree is also of size m minus 1. And this subtree is of size n plus 1 as well. So because of that, nothing can be a centroid on this side of the subtree. And therefore, these are the only two candidates for centroids, but this is literally a leaf, so it can't be a centroid, and therefore that works. Okay, so the solution is to... Okay, first of all, do the centroid stuff. How do we do the centroid stuff? So we say... Okay. We have multiple test cases, I assume, because this... Why not? Why did I delete it, actually? Let's just keep it. I didn't delete it. Okay. What are the bounds? 10 to the 5th. Okay, I can't appreciate that, though. They use 10 to the 5th instead of having annoying bounds that make it harder in other languages. Okay, let's focus. So, I'm just going to write standard graph stuff. Then we write some DFS. We can remove any edge, so let's just remove the one between 1 and 2 and add it back. Else we have more stuff to do. So okay, we will visit the higher centroid before the lower one, but we'll add the lower one before the higher one. If there are two centroids and we pick something as the root, then one centroid has to be a parent of the other because there's an edge. So the way we find a centroid is we just literally check everything, like if its subtree size is whatever. And we can just brute force check everything. Even though it doesn't actually matter. Yeah, we'll just check every node for being a centroid. And now what? So why? What the hell? Can't type anymore. So to see if this is a centroid, first we have to go down into all of its children and compute their subtree sizes. So if the child is a centroid and the parent is a centroid, we'll look at the child first. So it will be first in the vector. Rem size equals n minus size minus 1. Minus 1 because we include this vertex. If size less than or equal to n over 2. That's the same. That's the same thing as checking if it's small as possible. That is a weird definition of a centroid. That centroids that push back. If size equals 1, oh wait, size is less than or equal to n over 2, and the remaining size is less than or equal to n over 2, then it's a centroid, so be happy. If size equals 1, then it's a leave. A centroid by definition can't be a leaf because n is greater than or equal to 3, so that's fine. This is annoying implementation. Okay, so leaves.clear, DFS, let's see, centroids 0, centroids 1, cout leaves 0.first plus 1, not first. Then cout leaves 0.first plus 1, and then we reattach that leaf to the centroid, to the first centroid, or the second centroid. And that does exactly what I've illustrated. And I think that should work. What? Right. Okay, so first of all, centroids.clear, leaves.clear, I guess, even though it doesn't matter. Then we do edges.clear, so everything's reset. Perfect. Is that a warning? Okay, fine. I don't have the input. Boy, doesn't spaz out. Seg fault. Yep. Because I'm dumb. That would be stupid. To make sure we don't infinite loop. Still? What is it doing? What is it doing? Cout 7. Force it to flush the output. Did we get past the first test case, or did it just die? We don't get past the first test case. What's happening here? Okay. So DFS centroid 0, centroid 1. What happens in here? Using endl to force flush the output. Why are there no centroids? Oh boy. What the hell? Okay, so the problem is we're accessing vectors out of bounds. Why is this happening? Cout size, rem size, endl. There has to be a centroid. Every tree has a centroid. Oh wait, we don't include ourselves. Okay. Yeah, we don't include ourselves because we removed this vertex. Whoops. Okay, 1, 2, 1, 2, 1, 2, 1, 2. What's happening here? Wait, why is there only one centroid for both? Why is it always 1? Okay, 1 should be a centroid here, that's good. But then what? Should this be n minus size? Just n minus size? It doesn't make a difference, does it? Oh wait, this should be n minus size actually. But that still shouldn't make a difference. What is happening? One, 3, 2, 1. What? What is going on here? So we visit 4 or 5 first, then 5, then 1, 3. Oh wait, we're looking for the maximum subtree. Whoops. Okay, whoops. I totally remember how this works. 'worst equals max, worst rem. I totally remember how this works. So now the worst subtree has to be that, and the remaining size also has to be that because the parent is a subtree. Still doesn't work. Because we don't compile. Worst. Okay, what happens here? Do we have multiple centroids for both now? How? What? Why are we visiting everything so many times? What is going on here? So V304. What the hell is this? We should be like, this should be 10. We should be printing these 10 times, that's it. Oh, wait. Oh, wait. Oh, wait. Oh, wait. Okay, that's stupid. That is incredibly stupid. Okay, 1, 2, 1, 2, that's fine. Then 5, 2, 5, 1, that works. I can't open my... What happened to my computer crash? Did it actually crash? Oh my god. You guys see this right now? Like the taskbar is just gone. Did OBS crash too? I can't even submit my code now because it's broken. I can still use Chrome fine. Like my taskbar is literally gone. Can't do anything. Guess we'll wait for this to pass. I don't even know what I'm supposed to do right now. Because this also happened before the contest, and that is very annoying. You're gonna come back at some point? Any plans to? Any plans to let me submit? Guess we'll read D in the meantime. Given a sequence of n integers, you have to construct two sequences of length b of integers b and c with length n. Now two sequences b and c of integers. Let's satisfy for every I, bi plus ci is ai. B is sorted, C is reverse sorted. Wait, no. B is reverse sorted, C is... Wait, what? Why would they... Oh my god. Why would they do the comparison like this? Okay, B is non-decreasing, so... B is sorted. C is non-increasing, so it's reverse sorted. And you have to minimize the maximum number. Okay, come on. Thank you, program. Thank you, computer. Let's make sure this isn't stupid. Size equals 1, worst equals 0 for each edge. If it's not the parent, then DFS. Take the biggest subtree, add it to the size, and the remaining size is everything but this subtree. So if both of these are less than or equal to n over 2, we have a centroid. If size equals 1, we also have a leaf. So clear everything. Everything's cleared. Read in n, read in the edges, DFS, once. If there's only one centroid, we're done. Otherwise, find any leaf in the tree of centroid 0. Like any leaf. And then remove that leaf, and then attach it to the other centroid. That should be good. Did OBS crash? Okay. That's kind of scary. Wrong answer on pretest 2. Okay. What is with that? Also, wait, it crashed my folders. What the hell's going on? So make some big sample, I guess. 7. Oh, actually, wait. Make a line graph. 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8. Now what? 8, 7, 8, 4. That's fine. Eight, 7, 8, 4. Okay, let's make a star. 6, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. That should be good, because we just do whatever. The only hard case is when there's one centroid. Let's do the graph I was talking about here. So we will add 6 and it'll be so 1, 2, 3, 2, 2, 5, 4, 5, 5, 6. So 2 and 5 are these center vertices, everything else is attached to their respective whatevers. Okay, 4, 5, that's this edge, then add it to 2. Okay, so I'll read over my code once again, I guess. C into n for each thing, clear the edges. Okay, what we can do is we can do my classic trick of just copying in the samples again and again. Should print 4, 5, 4, 2 every time. It does. Okay, size equals 1, worst equals 0. For each edge, it's not the parent, remainder. Centroid 0 is the child. Right? So the fact that we don't clear the centroid shouldn't be a problem here because centroids 1 isn't going to change. Leaves aren't going to change. Obviously I just won't change. Is there something annoying happening here? We're doing the centroids right? Should be 4 and 1, that's 5 and 2, same thing. And 4 is a child of 1, a direct child. Print that. 2 and 1 are the centroids, 2 is lower. So that's fine. So I guess okay, for each edge, if it's not the parent, just keep checking. Force is less than or equal to number 2, so if the lowest subtree below is less than or equal to, and the subtree above is small enough, then we got it. If the size is 1, then it's a leaf. It has no children. And there's no other case when it would be a leaf, right? And we make a pair of it and its parent. Will centroid 0 ever be a leaf? It can't. Because then you have m minus 1 size, and that's not gonna work. Centroid's not clear. Ah! What is happening? N is 10 to the 5th. T is 10 to the 4th, that shouldn't matter. We didn't submit that, right? Okay. We didn't submit that. Okay, back to the drawing board. So let's think of it more arbitrarily. So we have two centroids and they're connected by an edge. Specifically, we'll say that there's some higher, so we'll say that this is at a higher depth than this. And Neither of these can be leaves. Am I finding centroids wrong? Maybe this conditioning is wrong. Ah. So if there's a vertex that splits all the subtrees into subtrees of size less than n over 2, then there's always going to be one centroid. Because any vertex in any of the subtrees can't be a centroid, because they'll be somewhat adjacent to the centroid that we have, and that, like the math works out there, I think. So it has to be exactly n over 2, and that only happens when n is even. And furthermore, it has to be exactly n over 2, and furthermore, they're connected. Be connected. So if the root is a leaf, that shouldn't make a difference because we don't care about all leaves. We just need a single leaf. We clear the leaves here. So now every leaf is going to be a child of centroid 0. So we can then attach it to centroids 1, right? So then once we do that, so we take some vertex, we delete its edge, and then we attach it to here. So we'll assume we move it over here. So now this subtree size, which used to be n, is now n minus 1. And whatever happened up here, which also, so we knew before that this is n. So whatever's going on here is also n minus 1. And of course this is 2. So any vertex in this side can't be centroid because these are n plus 1. Any vertex on this side can't be a centroid because this is also n plus 1. And so this isn't a centroid because it's a leaf. And this is still a centroid, and it has to be the unique one. Don't see why that would ever fail. So I guess there's something else that would happen. This is definitely going to be something stupid. So in leaves, we store the edge from it to its parent. Then we remove that edge. Then we add in the edge from that leaf to the second centroid. And in the way we compute the centroids, the lower centroid will be first, so the higher centroid will be centroids 1. Higher centroid will be centroids 1. assume a lot of people will solve this next. It seems like a simple problem. But what is going on? So this is attaching that leaf to here. But what we do is we attach this leaf to here. And that wouldn't make a difference, would it? Can't imagine it would. So we can just go with their definition of centroid. I don't see why it's different though. I don't see why it's different. Thanks. I don't see why it's different. But whatever they say. Is this what it wants? Okay, it's the same answer. Size equals 1, worst equals 1, etc. What was fixing? Okay, I'm taking a break from this problem. We're going to D. To minimize the maximum number in sequences B and C. So B is non-decreasing. Right, so B is sorted, C is reverse sorted. Why is AI negative? Why'd they do that? So the maximum here is 5. Then you reduce each of these by 3, and then the maximum is still 5. Where does 5 come out of? It's so weird. So then here the sequence will still be 5, and then when you increase that, it makes it worse. Okay. So let's say you have this. Let's make a new paint. Make a new one. Am I not able to make a new one? Can I just like open a duplicate? Yeah. It's not a good day. Okay. Well, we're gonna delete this then. Jesus. So let's imagine this sequence. 2, -1, 7, 3. Now let's say we have something like this. So we have x and y, and those are just whatever. So now, so this is the maximum that C will ever have, and whatever we have here is the maximum that this will ever have. So now what we have to do is we have to, let's say we transition here. So this goes down by 3, which means we need to make the sum of x and y less by 3. So we're not allowed to decrease x, which means we have to decrease y. So I think the best thing we want to do is make this y minus 3 and keep this as x. Because otherwise, what did I do here? I have some weirdness. Wait, why is that 5? Oh, because the difference is 8. Okay. So this should be y minus 3, because say we did something else. Say we made this x plus 1 and y minus 4. Like that's just strictly worse, because we've already hit the maximum of y, but the maximum of x is going to be at the end. So we want to keep x as low as possible, and this only decreases y, so like it's not really going to help us. So the best thing we do is if the difference is less than 0, then we just like chill. Otherwise, the difference is greater than 0. And that's kind of annoying. Or is it? No, it's not. So now the difference here is -3. The difference here, 7 minus -1, is 8. So we can't increase y. So we have to increase x. And so we increase x to x plus 8. And y to 1, we keep y as it is. Again, by the same argument, if we increased x to anything higher, say x plus 9, that would be stupid. So we'd screw ourselves over. Now the difference here is -4. So here we have x plus 8 again, and y minus 7. Okay, now so x plus 8. So now we have like some numbers. So we know that x plus y equals 2. We know that x plus y plus 1. Okay, that's stupid. Of course, that's obvious, but why is that helpful? So now we need to find the optimal choice of x and y. And subject to x plus y equals 2 and minimizing the maximum of these two. That's the formalness, whatever. And the way we basically come up with these numbers is we sum up the positive and the negative differences. and we just treat them separately. So we want to make y as large as possible without making it too big, I guess. That's what we end up doing. So what is the optimal choice for y, given that x plus y have to be equal to 2 and y is as large as possible? I think the difference between the two should be as big as it can. So actually, in the sample, x here is -3 and y is 5. X here is -3 and y is 5. And the reason that works is because both of these are eventually going to touch 5 at the end. Because here we get x plus 8 is equal to 5, and y is as big as it can when it starts. So, yeah. Okay. So what do we do with that information? So the update's not a problem. We can do a thing called a difference array, and it ends up being cool. But what else happens here? So let's assume we have 0, first of all. And then okay, now we want to make x. Actually, we don't care about the negative sum. All we care about is the sum of positive differences. So let's say d is the sum of all positive differences. I need a new color here. D is the sum of all positive differences. Then basically, if d is, let's consider the floor of d over 2. I think the best choice for x and y are negative d over 2 and then positive d over 2, and then actually ceiling d over 2. And then these are going to sum to 0 or 1, I guess. There's some annoying parity stuff going on here. Okay, what is going on? So I'll put this here, and then we can clear the code. Let's get a refresher, and let's. It did open them just like years later, I guess. I don't know. Alright. So we have some value d, and we want to do some stuff to it. Actually, why don't we just start off with this? This should be simpler. So let's have x be negative. Let's have x be negative d, and then y be 0. So now the difference between these is d. So then let's say, come on, a0 equals k. Then for floor k over 2 times, we'll either like increase or decrease by 1 depending on if k is negative or positive. And then if k, let's say k is less than 0, negative, and k is odd, then we just decrease one more of these by 1, but we can't do both. Yeah. And k is greater than 0 and odd, then we have to increase one of these by 1. So the answer is actually, I think it's simple. It's just, does it matter what d is? Yes, it does. Actually, what we care about is the quantity k minus d at this point. So I think it might just be the ceiling of k minus d over 2. Ceiling being defined carefully for positives and negatives. That's interesting. Oh, come on. Don't crash again, taskbar. But it's going to. Because my computer... What? Are you guys seeing this? This is so stupid. Okay, let's do some math. So yeah, I think the answer is just the ceiling of k minus d over 2. Let's... Okay. But maybe not ceiling, actually. Not necessarily ceiling, it depends on whether it's positive or negative. Yeah. Okay, so... Sorry, this should be ceiling of k plus d. Because we start off with negative d and we have to change it by k. Okay, so... then we'll use b as the, or we'll use diff. So for li equals 0, I is less than n, I plus plus, diff I equals a, I plus 1 minus ai. This is a difference array, and we'll just directly compute the value of d. If diff I is greater than 0, d plus equals diff I. Now, we read in queries. Now, the cool thing about this is that we don't actually care about the elements. All we care about is the differences between them. So let's see what a query has to change about a difference array, right? So on this difference array, we have -1, 3, 2. So say we add 2 to all of these elements. Then the only difference that changes is this one, and it increases by 2. Let's say we add 2 to these elements. The only difference that changes are these two. This one gets increased by 2, and this one gets decreased by 2. Because this one gets bigger, and this one gets bigger. So essentially, if L is greater than 0, if diff L minus 1 is greater than 0, d minus equals diff L minus 1, then diff L minus 1 plus equals x, because we add it, and then if L minus 1 is greater than 0, then we add it to d. Then we say if r is less than n minus 1, if diff r is greater than 0, d minus equals diff r minus equals x, diff r is greater than 0, d plus equals diff r. Val equals, what is it? So it's a0, oh wait. So if L equals 0, A 0, a0 plus equals x. That matters, because we also have to keep track of the first element. That equals a0 plus k over 2. Or plus d over 2. So then, if a0 mod 2 is not equal to 0, then if a0 is greater than 0, we have to increase val. I think that should work. Should work. The other one should have worked too, but it didn't. LD. Make D global. Test cases. Five, 5, 6. Great. And what's with that? So why is this 2? Is this the thing that we have to do? Oh wait, this should be, whoops. This should be the times we have to increase. A0 plus D mod 2 is not equal to 0. Yeah. Because that's the amount of times we actually have to increase the value. Because we want them to sum to that. Or not. Okay, why? So we're getting the first one wrong. Maybe that's a thing. Shouldn't go up to n. Come on, what is happening? I can't click on it. I can't click on anything. What is going on here? Oh my god. My computer is actually dying. I don't know what to do. I don't know if you can even hear me right now. So if you can, I will wait until this starts again, or my computer crashes, whichever comes first. And come on, I was literally just about to test it on the thing that I wanted to see if it worked. That's so annoying. Still, wait, why am I able to move the mouse around but I can't do anything else? Like, none of the buttons work. Nothing is happening. Can I do anything? Can't do anything. Does this work? Can I even open Task Manager? Can I do anything? Okay. Guess we'll turn off the computer. Wait. The time just updated. What the hell is going on here? I can do that. That's the only thing I can do. Alright, we're turning off the computer. Rip the recording, I guess.